Let's say we have an object moving in a circle. Let's say it's going counterclockwise, like this. The outer circle there is the path of this particle. I'm going to draw 4 arrows, okay, and I want you to tell me what those 4 arrows can represent, right? So the first arrow is going to go, say our object is at this point in the circle, okay? The first arrow is going to go in toward the center of the circle. The second arrow is going to go along the path of the circle. The third arrow is going to go like this. It's a tangent to the circle. And the fourth arrow is going to go out like this, outwards. I'm going to label these 1, 2, 3, and 4. Now, I want you to pick out which of these arrows represents the following quantities. Firstly, the velocity of the object. At that moment in time, this moment in time, right here, which way is the velocity of the object pointing? Is it 1, 2, 3, or 4? Which one is it, Tom? It's 3, yes. The velocity of the object is 3. An object will always go in a straight line at a constant speed until acted upon by an unbalanced force. In the absence of an unbalanced force, this object is going to go in a straight line. So at any given moment in time, it is traveling in a straight line. It's just that it's pulled away from that straight line because of a centripetal force, the force that pulls it toward the center of the circle. So yeah, we're going to say the velocity of this object is number 3. What about the acceleration? What number represents the acceleration of this object? How can we even say there's an acceleration? If we're talking about uniform circular motion, then we're talking about an object that's going in a circle at a constant speed. How can there be an acceleration if we're not changing speed? Okay? Yes, we're changing direction, and acceleration is dependent upon speed. Yes, it is, but it's also dependent upon direction. It's not the rate of change of speed, it's the rate of change of velocity, which includes both speed and direction. Parker, you said it's number 1. It is number 1. Okay, the acceleration points toward the center of the circle. We'll justify that in a second here. Which way? What about the force? Which way is the force pointing? Well, if the acceleration is pointing towards the middle of the circle, which is number 1, then the force is going to point toward the center of the circle as well. That's going to be number 1 as well. Okay, number 2 would simply represent the path of the particle. It's not the velocity. Okay, we could say it's the speed, I suppose. Okay, 4 doesn't really represent anything because nothing is really pointing outwards, not in terms of a real force, at least. All right, let's justify that the acceleration is toward the center of the circle. I'm going to redraw this circle. Object is going in a circle. At this moment in time right here, the velocity is this way. At this moment in time, the velocity is, let's say, this way. We're going to call the blue one VI. We're going to call the green one VF. If I want to find the direction of the acceleration, then I want to find the direction of the change in velocity. Because acceleration is VF minus VI over t, or delta V over delta t. If I can find the direction of VF minus VI, then I know the direction of the acceleration, therefore the force. Now, I don't know how to subtract vectors, but I do know how to add vectors. So I'm going to say delta V is not VF minus VI, but rather I'm going to say it's VF plus negative VI. That's the same thing, right? Like 6 subtract 2 is the same as saying 6 plus negative 2. VF minus VI is the same as saying VF plus negative VI. Well, let's replace the VI here with a negative VI. So let's add up VF plus negative VI. The sum of those vectors, or the resultant vector between those two, is going to be this. That's going to be delta V, VF plus negative VI, or VF minus VI. Which way is it pointing? Inward, toward the center of the circle. Well, if delta V is inward toward the center of the circle, then the acceleration must also be inward toward the center of the circle, as does the centripetal force have to be inward toward the center of the circle. Look, this is where the term centripetal comes from. Centripetal means center seeking. So if you see that word centripetal force, centripetal acceleration, even if you don't remember which way that force is pointing, you know automatically that it's got to point toward the center of the circle because that's what the word means. Does that make sense? If I swing those keys around my head again, and I happen to let go, which I'm not going to do because I don't want to hurt anybody. If I happen to let go, where are they going to go? Straight line. Not outwards, right? They go in a straight line. Here, I'll try to do it. No, I won't. Come on. I'll release it at the wrong spot, and then Helios gets smacked in the head by these keys, and I'll s- and then I'll knock over her bottle of Pepsi, and it's just going to be a big mess. So I won't do it. But you know that it's going to go off in a straight line, right? Okay, you know that when I circle these keys around, these keys are not going to go off like number 4 here. These keys are going to go off like number 3. If I'm going around to turn on a road, I told you guys about the time when I was a teenager and driving this delivery van, the dry cleaning company that I worked for. Remember that? And I'm going around this turn on some ice, and I skidded off the road and hit the guardrail. Not hard, not crazy hard, but I didn't skid off like this. I didn't hit a patch of ice and then do this, right? Everybody knows that when you skid off the road, you're going to go off in a straight line like this, okay? Because my velocity is always a tangent to the circle. My acceleration is inward, my force is inward, but my velocity is a tangent to the circle. Does that make sense? All right. How do we determine what that velocity is? We can use an equation that we learned yesterday. V is equal to 2 pi r over t. That's on your data sheet. But where did the 2 pi r come from? That 2 pi r is a math thing. It is the circumference of a circle. So if we're talking about v equals d over t, d being the circumference of a circle, then t would be big T, the period, which is the time for one revolution. The distance for a revolution, the time for one revolution. Now we can find the period, the time for one revolution, if we want to, by dividing the time by the number of revolutions. There's another term that's like period, though, frequency. You remember how to find the frequency? It's the number of revolutions divided by the time. It's the exact opposite. Now, if you take a look at these two equations, you can see that they're closely related to each other. In fact, if we take the frequency and flip it over, take the inverse of it, then we'll get the period. These four equations are all important, but it's only the two that are boxed off that are on our data sheet. This is more of a definition, as is this. So we just kind of got to remember those ones. The first one and the last one are on our data sheet, however. Finally, two more equations. One for centripetal acceleration. V squared over r. What does V stand for? How fast it's moving, right? The velocity of the object. Is that right? Is that right? What's wrong? Yeah, it's not the velocity of the object. There's no little vector sign over it, right? The velocity is always changing because the direction is changing. It's not the velocity. It's the speed of the object in meters per second divided by the radius of the circle. That one's on our data sheet as well. Centripetal force. Well, we could say it's m times a, but if a is v squared over r, then m times a is m times v squared over r. That one's on our data sheet as well. What units, by the way, would centripetal acceleration be in? Meters per second squared, yeah. What units would centripetal force be in? Newtons, of course, right? Make sense? So let's take a look at the questions that we had for homework here on worksheet number 20. Let's take a look at questions 4, 5, and 9 here, starting with number 4. It says the Earth makes one revolution around the sun every 365.25 days. The orbital radius of the Earth is 1.5 times 10 to the 11 meters. That means the distance between the Earth and the sun is 1.5 times 10 to the 11 meters. It's a big distance, right? From the center of the Earth to the center of the sun, 1.5 times 10 to the 11 meters. What's the acceleration of the Earth as it orbits around the sun? Expecting a big number or a small number for this? Big? Okay. I'm expecting a fairly small number, actually. Okay. I think that the Earth is going to be moving very, very fast around the sun. I mean, think about that. That's the radius of the circle, and it makes it all the way around the circumference in a year. It's going to be traveling pretty darn fast. But as far as the acceleration goes, I don't think it's going to be very big because the radius is so big. That makes sense? The bigger the radius, the smaller the force needs to be, and therefore the smaller the acceleration to hold it in orbit. So I think we're going to get a small number for this. Okay, we'll see. What do we have given to us here? The Earth makes one revolution around the sun every 365.25 days. Tell me what that 365.25 days is. Is that big T? Is that little t? That's big T. That's the time for one revolution. So that's big T, the period, the time for one revolution. 365.25 days. Although we're going to want to convert that to seconds, right? We don't want to be in days here. Convert it to seconds. Let's multiply it by 24 to get days. Then let's multiply it by 60 to get minutes. 24 to get hours, I should say. Then by 60 to get minutes. And then by 60 again to get seconds. When I do that, I end up with a value in seconds of 315,576.00 seconds. That's a lot of seconds, eh? But you think, like, in this class, about 5,000 seconds will go by in this class alone. Well, it doesn't take very long to add for the number of seconds to add up, right? If in this class alone, 5,000 seconds will go by. So that seems like a reasonable number. The radius here is 1.50 times 10 to the 11. And the centripetal acceleration, that's what we're looking for here. We want to find the centripetal acceleration. Let's say A is equal to V squared over R. But look, we don't know what V is, so we got to find it. V is equal to 2 pi R over T. Hey, we know what T is. This is good. 2 times pi times 1.5 times 10 to the 11 divided by T, which is 315,576.00. Now let's do the math on this one and see what we end up getting. 2 times pi times 1.5 times 10 to the 11. Now let's divide that by 315,576.00. We're going to get a value of 29,865.319 meters per second. Like, think about this, what that means. The Earth right now is traveling at 30,000 meters per second as we stand on it. Yeah, it actually varies a little bit depending upon where it is in relation to the sun, but it's more or less 30,000 meters per second at all times. Why don't we feel that? Why don't we notice that? Yeah, it's not a constant velocity, but it is a constant speed, more or less, right? Like, how many people went somewhere in an airplane at spring break? Yeah? So you went to Costa Rica. Yeah? Where'd you go? You went to Costa Rica too? So when you guys were on the airplane, like, you didn't notice when you were traveling at 900 kilometers per hour in the air, right? Like, it just was normal, right? You went to take a drink and the water or Coke didn't splash all over the place, right? It was as if you were at rest. What you noticed is when you were speeding up on the runway and when you were slowing down on the runway, right? That's when you notice it. When you're traveling at a constant speed, you don't notice 900 kilometers per hour or 30,000 meters per second. You notice if the Earth was to speed up suddenly or slow down suddenly. Yep.
Why is it that, like, if you're in a car...
Let's sub that number in now. 29,865.319. Square that. And now divide that by R. We get 1.50 times 10 to the 11. Let's see what we get here now. I predicted a small number, but let's see. Let's square this number for speed. Divide it by 1.5 times 10 to the 11. And we get, sure enough, 5.95 or 5.95 times 10 to the negative 3. So yeah, sure enough, that's a small acceleration. It doesn't take a great deal of centripetal force and acceleration in order to keep the Earth in orbit around the sun, because its radius is so big. You guys know if you go around a turn in a car, the bigger the radius, the easier it is to stay in the circle, right? You go around a turn on a bike, the easier it is to stay on the track if you have a bigger radius. The smaller the radius, the harder it is, and the bigger the centripetal acceleration of force would have to be. Yep. Yep. Okay, let's take a look at number 5. Similar to number 4, the moon makes 12 revolutions around the Earth every 1 year. Calculate the centripetal acceleration of the moon as it orbits around the Earth, that should say. What do we got here? We get the number of revolutions is 12. What's this 1 year? By the way, 1 year is We already calculated that. 315,57600 seconds. Is that going to be big T or little t? Little t is just any time, right? Big T is the time for one revolution. What do we got here? It's little t, right? Time for, well, however many revolutions. We have the radius here, although we do have to check our data sheet to find the radius. On the back of our data sheet, it says the average Earth-Moon distance is 3.85 times 10 to the 8 meters. And we want to find the acceleration, the centripetal acceleration. We're going to say v squared over r, but we don't know what v is, so let's find that. 2 pi r over t, but this time we don't know what t is, so we got to find that. What are we going to do for t? Is it 315 over 12, or is it 12 over 315? In other words, time over revolutions, or revolutions over time? Megan, what do you think it is here? Is it time over revolutions, or is it revolutions over time? Yeah, it's time over revolutions. So it's 315,57600 over 12. That's going to give us a value of, what is that going to give us? 315,57600 divided by 12 gives us a value of 262,9800 seconds. Okay, we're getting there. 2 times pi times 3.85 times 10 to the 8 divided by that number. That's going to give me speed now. 2 times pi times 3.85 divided by 262. Oh, look, the moon is going a lot slower. Right? You would expect the moon to be going a lot slower, right? The radius of the moon's orbit is a lot less than the radius of the Earth's orbit. So there's one reason to believe that the moon is probably going slower. Right? The faster it's going, the bigger the radius is going to be. So we don't know how big it's going to be, but we know we expect it's going to be a smaller speed for sure. And sure enough, it is quite a bit smaller. 919.8518 meters per second. Now, we just sub that in here and square it and do our thing like we did in the last question. What's R 3.85? We're going to expect a fairly small acceleration here too, I think. Not sure exactly what, but let's take that number, square it, divide it by 3.85 times 10 to the 8. Gives us a value of 2.2 times 10 to the negative 3. So sure enough, a fairly small acceleration there as well. And finally, let's take a look at number 9 here. It says a 2.5 gram insect. Grams. We don't want grams. Makes 2 turns around a 200 centimeter diameter circle in 3 hours. We don't want centimeters. We don't want hours either. What's the force experienced by the insect during this time? Let's write down some givens here. My mass is 2.50 grams, which I convert that to kilograms, divide by 1,000. I end up getting 0.00250 kilograms. The number of turns, or the number of revolutions, is 2.0. 200 centimeters, I'm going to convert that to meters, right? 2.0 meters, what's that? Radius? Is that radius, R? Karen? It's diameter. I don't want the diameter. I want the radius. The radius is 1.00 meters, right? The radius is half the diameter. Man, how easy is it to miss that, hey? We want to find the force here. So we're going to say F is equal to, what, mv squared over r? But we don't know what v is, so we say v is equal to 2 pi r over t. Oh, wait a sec. There's a time here. 3 hours. Is that big T or little t? What is it? Yeah, it's a little t. 3 hours, which by the way works out to be 10,800 seconds. Multiply by 60, multiply by 60 again. Okay, we can do this now. 2 times pi times 1.00 divided by the time of 10,800. That's going to give me speed. Let's find this now. 2 times pi times 1 divided by 10,800. 5.8178 times 10 to the negative 4, was it? Yep. It's going pretty slow, right? No, something's wrong with that. Oh, yeah, you're right. Oof. I went 2 pi r divided by little t, right? Should be 2 pi r divided by big T, right? So let's find big T. Let's find big T. It's going to be, Megan told me the right way last time. Who's up this time? Queen, is it going to be 10,800 divided by 2, or is it 2 divided by 10,800? Right. Which is going to give me 5,400 seconds. And that's going to give me is it 1.1164 times 10 negative 3 seconds, meters per second? Everybody get that? Yes? That's a pretty slow speed, right? But look, this, like, think about this. This insect is taking 3 hours to go around this turn. There's a 2-meter diameter, so it's going pretty slow. Yep. No, that's the speed, right? 2 pi r divided by the period. That make sense? And now I'm going to say 0.00250 times v squared. Oh, I like it. I like this. I like it when r is 1 meter. Why? I don't need to divide by 1 then, right? So let's take that number that we got for speed here. Let's square that, and let's multiply it by 0.0025. Gives me 3.3 times 10 negative 9. Is that right? .4 it should be times 10 negative 9. Just seems so small. I mean, really, I should expect a small number. I just didn't expect quite that small. I should expect a small number because you got a really, really light insect going really, really, really slow. How much force is required to keep this insect from falling off? Not much, right? In other words, the centripetal force is going to be pretty small here. You still comfortable with that question? You can do that question. You're going to be absolutely fine on tomorrow's quiz. But just to make sure that you're going to be fine on tomorrow's quiz, I'm going to put up a little fake quiz. You're going to do that in class. We'll see how that goes for you, and then we'll move on to the next topic. At the top of this, it says quiz number 19. It's really fake quiz number 19. You're going to just do this on a piece of paper, and then we'll see what we get. Okay, look up here. We're going to do these questions now. Calculate the acceleration of the outer edge of a record of an old record player rotating at 33 RPMs, revolutions per minute, if the diameter of the record is 30 centimeters. A couple things you got to watch out for here. First of all, this is centimeters. We want meters. This is RPMs. We want RPS, revolutions per second, or what's another unit that we can call the same thing as RPS? Hertz, right? Hertz. That's typically what we see it written as. Also diameter. We don't want diameter. We want radius. So let's say the frequency here is 33 RPMs. We'll divide that by 60 to get 0.55 RPS, or 0.55 hertz. We see a radius here, not a diameter, but a radius of 0.15 meters. and we want to find the acceleration, the centripetal acceleration here. So we're going to say A is equal to v squared over r. But we don't know what v is, so we'll find it. I erase it, and then I write down the same mistake. Here we go, v squared over r. So let's find it by saying v is equal to 2 pi r over t. But I don't know what the period is. How did I find the period? Aoife, how do I find the period given the frequency, 0.55?
Oh, using the equation frequency, 1 over frequency.
Yeah, 1 over f. 1 over 0.55. And I think, does that work out to be 1.8 or something like that?
1.818.
1.818? So that's the time for one complete rotation here, one complete revolution. We're going to say 2 pi times 0.15 over 1.81818. Let's figure that out on the calculator here now. 2 times pi times 0.15 divided by 1.81818. 0.5184. Which we're now going to sub into here, 0.5184, square it, and then divide it by r, 0.15. Take that number, square it, divide it by 0.15, get a value for centripetal acceleration of 1.79. 134. Now I'm going to round that to 2 digits to give me 1.8 meters per second squared, but you'll see why in a second, why I left the unrounded number there written down. Question 2 says, what's the centripetal force? There's 2 ways I can do this. There's the quick, easy way, or there's the way that takes a little bit more work. We could say F is equal to mv squared over r, right? We got m, we got v now, we got r, we can do this. Or we can just say, why don't we just do this? F is equal to m times a. If you've got the centripetal acceleration, you should be able to find the centripetal force by just multiplying the mass, which is 0.235. Oh, be careful here. 0.235 grams, 0.235 times 10 to the negative 3 kilograms, times the acceleration we just found, 1.79134. Gives us a value of 2.42 times 10 to the negative 4. So, hey, listen, that's a pretty small centripetal force, right? It's not so small because the radius is so big and it doesn't have to provide much centripetal force to keep it in orbit there, but rather, look, this is a 0.235 gram speck of dust. How much force is needed to keep that going in a circle? It wants to go in a straight line, but you don't have to push on it very hard to keep it from going in a straight line. I want to do one more example with you here. Just got to find the example here. Here it is. It's question number 10 on your worksheet. The worksheet that we checked over at the beginning of class 1 through 9. I'm going to do question number 10 as an example. It says an 1,800 kilogram truck is traveling at 90 around a turn. There's a coefficient of friction between the truck's tires and the road of 0.8. What's the minimum, it should say, the minimum radius of the turn so that the truck does not skid off the road? Think about the typo there, right? If I left it as maximum, there is no maximum, right? The bigger the radius, the wider the turn, the less likely you are to skid off. So it's not a maximum radius that you can go around. It's a minimum radius. The tighter the circle, the harder it is to stay on the road. You know that, right? The tighter the circle, the harder it is to stay on the road. So we want to find out what that minimum radius is. Here's what I want to do. I want to say FC, the centripetal force, is equal to FF, the centripetal force. Remember, the centripetal force is always caused by something. Here it's caused by friction. Why don't we just set them equal to each other? If they're equal to each other, why don't we set them equal to each other? mv squared over r is equal to, do you guys remember the equation for friction force? Mu times the normal force, which in this case, assuming we're a flat horizontal surface, would just be m times g. Do you see a way to simplify this a little bit? Make this a little bit easier? Yeah, you can cancel out mass because it appears in both terms, right? Take out the mass. What does that tell us? An 1,800 kilogram truck, a 900 kilogram smart car going around a turn, doesn't matter. Doesn't make any difference. You don't design a road for the particular car that's driving on the road. But you design a road for the speed that those cars can be traveling and for the friction that acts between the tires and the road. That make sense? Doesn't matter whether it's a little car or a big car. The mass cancels out. So I've got v squared over r is equal to mu times g, and we're looking for r here. So take that up by multiplying. Mu times g times r, and then we take the mu g down by dividing. V is, we don't want 90 kilometers per hour, rather we're going to convert that to 25 meters per second. Divide it by mu, which is 0.80 times 9.81. We should put brackets around everything on the bottom there, right? 25 squared divided by bracket 0.8 times 9.81. That is not right. What have I done wrong there? No, that could be right. Yeah, that could be right. 79.6 or 80 meters. Is that okay? So you're going around a turn like this, you skid off the road. You make the turn wider like this, you're less likely to skid off the road, right? It requires less centripetal force to keep you on that path. Designing a highway, probably going to want to do a calculation like this, right? To determine how wide the turn should be in order to not skid off the road. Does that make sense? Okay, take a look at number 11 yourselves at your desks right now, please. Okay, let's have a look at this. We're once again going to say FC is equal to FM. Sorry, not FM. I'm thinking of a physics 30 thing. The centripetal force equals the magnetic force. Hey, next year, when you take magnetism in physics 30, you're going to know that FC is equal to FM as well, right? FC is equal to FF here, or mv squared over r is equal to mu times the normal force, which, look, if it's on a banked surface or something like that, like a banked turn like on a racetrack, then the normal force isn't going to be m times g, right? The analysis becomes more complicated. But if it's a nice flat road, horizontal road, then the normal force is m times g. And then it becomes relatively straightforward. Mass cancels. Looking to solve for coefficient here. So the g goes down by dividing. I get mu is equal to v squared over r times g. Now be careful here because some people, I saw two people forget to square that speed. When you calculate speed in meters per second, 40 meters per second gives you 11.111 meters per second, divided by r, which is 30 times 9.81. And when we do that math, I think it was 0.419. 0.419, and there are no units associated with coefficient of friction.